The first part of this question involves a proof by induction that the sum of the first n natural numbers is given by this formula here. Now this was covered in another video in the section on proof by induction, so I won't go through this proof now. In this next question we can use the previous result or use a different approach to prove that the sum of the first n even natural numbers is given by n squared plus n. Okay, so I'll start by using the previous result. So this is what we saw previously. The sum of the first n natural numbers is n into n plus 1 over 2. Now, here we have the first n even natural numbers. Okay, so this is n equals 1, this is n equals 2, n equals 3, and so on. This is the nth one. So you can see the rule, we just multiply by 2. So to generate all the even natural numbers, we just multiply all our natural numbers by 2. And so that means that if we simply multiply both sides of this by 2, we'll have the sum of the first n even natural numbers. So there it is. Now the other way to do this problem is to recognize that we have an arithmetic series here. The first term of the arithmetic series is 2. The common difference between the terms, well, you can just take the second term and subtract the first term. 4 minus 2 is 2. And the number of terms that we want to sum is n terms. You can see that clearly. If we match up the numbers, natural numbers, with this series here, you can see that 2 1s are 2, 2 2s are 4, and so on. So we have n terms here. So we want s sub n. Now for a general arithmetic series, n sub n is n over 2 into 2a plus n minus 1 times d. In our situation, a is 2, d is 2, so we just plug in. We get a 4 here, a minus 2 here, 4 minus 2 is 2, and we get a 2n. We can factorize out this 2, out a 2, and divide by this 2 here, so we're left with 1 plus n, or n plus 1 inside the bracket. Using the results from A and B, shown here, find an expression for the sum of the first n odd natural numbers. Now here is the approach that we are going to use. Suppose that we want the sum of the first 4 odd natural numbers. Well, as we know, those are the numbers 1, 3, 5, and 7. Now, what we do is we take the sum of the first 8 natural numbers, that's 1 plus 2 plus 3 plus 4 as far as 8, and subtract away the sum of the first 4 even numbers. So we just generalize this procedure. Okay, let's suppose we want the sum of the first n odd natural numbers. Well, we consider the sum of the first 2n natural numbers. Okay, because we had to double 4 to get 8. So in general, if we have n odd integers, we need to consider the sum of the first 2n natural numbers and subtract from that the sum of the first n even numbers. Okay, so here I'm showing the sum of the first n odd natural numbers. Now, we don't have to worry about the form of the nth term here. You don't have to worry about what that looks like. You know, I've just written down the first 4 of them, but it continues on in general, of course. Here we have the sum of the first 2n natural numbers. Well, that's quite easy to see what the nth term, or the 2nth term I should say, is going to be. So we have 2n natural numbers here. And here we have the sum of the first n even numbers. Okay, and that's what we have up here. We have an expression for that. This thing here is just n into n plus 1. That's worked out from part B. What about this thing here? Well, we can use part A. But this is the sum of the first n natural numbers. We want the sum of the first 2n natural numbers. So we replace n here with 2n. Simplifying, we get n squared. Now here are some examples as a check. S1 stands for the sum of the just the first odd number, which is 1, and that is indeed 1 squared. Okay, so the rule is that we should get is n squared. The sum of the first two odd numbers should be 2 squared, and that's, as you can see, correct. The sum of the first three odd numbers should be 3 squared, and so on. Now, if you cannot use the results of A and B to prove this result, you could just do it by using the fact that the sum of the first odd natural numbers is an arithmetic series, and the first term is 1. The common difference is 3 minus 1, which is 2. So you plug those values for A and D into the formula for the sum of the first n terms of an arithmetic series, and you'll see that you'll get n squared. The nth term of a sequence is t sub n equals ln of a to the power of n, where a is positive and a constant. Now, as a brief aside, I just want to mention why a has to be positive. I may have done this before, but I'll just do it again. Now, we're getting the ln of a to the power of n. That means log to the base e of a to the power of n. We've seen before that e is roughly 2.71, etc. E is a positive number. Let's suppose that ln of a to the power of n is x. So what does that mean? It means that e to the power of x is the argument of the log function, which is a to the power of n. Now, since e is a positive number, it's plus 2.71, etc., e to the power of any number x is going to be positive. Okay, so for example, if x is minus 3, we get e to the minus 3. Well, that's positive because that's just 1 over e to the power of plus 3. So x can be negative, and we still get a positive result. So this thing here has to be positive because it's equal to e to the power of some number. And to ensure that this is always positive, we have to make sure that a is positive. Okay, a is going to be raised to the power of an integer. Well, a natural number actually, a positive integer. Okay, n equals 1, 2, 3, etc. N is just a number of the term of our sequence. Okay, now we want to write down t1, t2 and t3. Well, let's look at tn. We can use one of our rules of logs to rewrite this as n multiplied by ln of a. So the rule that we're using here is that log of something raised to a power, a to the power of n, we can just multiply in front by the power. We can just bring the power down in front. And it doesn't matter what base this log is. It could be base 9 or base 10 or any base, or base e in this case. So we have a sequence given by this formula here. But this is a very simple formula. A is a constant. It doesn't change. So that means that ln of a, the log of that constant, is another constant. So the only thing that changes in this is n. So anyway, let's write down t1. Well, we just plug 1 in for n. So we have 1 times ln a, it's just ln of a. t2 is 2 times ln of a. And t3 is got by plugging 3 in here, so we get 3 times ln of a. Okay, I've just rewritten our 3 terms like this here. Now, to show that these 3 terms are in arithmetic sequence, we need to take the second term and subtract the first term, see what that result is, and then take the third term and subtract the second term, and hopefully these two results are the same. And that's very easy to see here. t2 minus t1 is 2 ln of a minus 1 ln of a. Well, that's just 1 ln of a. And over here, t3 minus t2 is 3 ln of a minus 2 ln of a. That's just 1 ln of a. So we can see that the difference between these two terms is the same as the difference between the next two terms. So that tells us that the first 3 terms are in arithmetic sequence. And we also see that that difference, if we want to call it d, is ln of a. Now in the next question we want to prove that the entire sequence is arithmetic. Well, I mean, we can do a formal proof, and that's what we will do, but it's very clear that this sequence is an arithmetic sequence. You know, the next term, t4, is got by plugging 4 in for n. That's just going to give us 4 ln a. Okay, that's t4, and you can clearly see that we could have got this fourth term by just adding d, that is ln of a, onto the third term. 3 ln of a plus 1 ln of a will give us 4 ln of a. And similarly for the fifth term, if we plug 5 in, we get 5 ln of a, but clearly that's the same as just adding ln of a onto 4 ln of a. Anyway, even though it's clear that we're dealing with an arithmetic sequence, let's go through the formal proof. So to prove in general that a sequence is arithmetic, we have to look at the nth term and subtract the n minus first term, and that should give us a constant. That is a number that doesn't depend on n, and that constant is what we call d, you know, the difference between two consecutive terms. So here we're dealing with two consecutive terms, but we're dealing with the difference of two general consecutive terms, the nth term and the term previous to it, which is tn minus 1, of course. The term previous to tn minus 1 will be tn minus 2, and so on. Okay, so let's just calculate this thing. We should get something that does not involve n. We should just get a number, which is, you know, a constant. So the nth term is n ln of a. That's what we were given, of course. Now what's the n minus first term? Well, we just replace n with n minus 1. So we just have this here with n minus 1 in for n. You know, we can factorize out ln of a here. So we get n minus bracket n minus 1, all multiplied by ln of a. Okay, if we factorize out the ln of a, and of course if we solve what's inside the bracket here, the n's disappear, and we're left with 1 times ln of a, or just ln of a. So that's our constant. A is a constant, so ln of a is a constant. That's what we were given. So that's the proof that the difference between any two consecutive terms is a constant. So we have an arithmetic sequence. And d is, the common difference is ln of a. Find the value of a for which t1 plus t2 as far as t100 is 10,100. Okay, so I've written out these terms explicitly. You know, the nth term is n times ln of a. So ln of a is some constant that we have to find, and when we have ln of a, we know what a is. Clearly we can factorize ln of a out of the left hand side, and in here we have an arithmetic series. The first term t1 is 1, the difference is 1 because 1 plus 1 is 2, etc. And we have 100 terms, so n is 100. By the way, the first term, as we know, is also referred to as a, but this a is not the same as this a here, of course. This a is just a label for the first term. You know, these a's have different meanings, so that's why I didn't write it down that time. But anyway, the formula for the sum of the first n terms of an arithmetic series is n over 2 into 2a plus n minus 1 times d. So you plug 1 in for a and 1 in for d and 100 in for n, and calculating this you get 5050. So now we found that this quantity is 5050. We divide 10,100 by 5050 to get 2. So ln of a, of course, means log to the base e of a, and writing this as an index or equation with a power, e to the power of 2 is a. So we put e to the power of 2 here. That's approximately 7.389. Verify that for all values of a, the sum of the first 10 terms of the series plus 100 times d is the sum of the next 10 terms of the series. D is the common difference of the sequence, so d, as we know, is ln of a. Here is what the left hand side looks like. T1 is ln of a, T2 is 2 ln of a, and so on as far as T10, which is 10 ln of a, and we want 100 times d, which is 100 ln of a. Let's look at the right hand side. T11 is 11 ln of a, so remember Tn is just n ln of a, so T11 is this with n replaced by 11, and so on as far as T20. So is there any easy way to go from this expression to this expression here? Well, we could simply add all the numbers from 1 to 10 and add that result onto 100, and then just add all the numbers from 11 up to 20 and see if those values are the same. The ln of a is just a factor that can be pulled out. Now we could do something clever here and write 100 ln a as 10 ln a plus 10 ln a, and so on. We have 10 terms here. 10 tens are 100. And what we could do next is take each of these terms and add it to each term over here. So that's going to give us 11 ln of a. And if we take this one here and add it onto this one here, we get 12 ln of a, and so on. We keep doing that because we have 10 terms here inside the bracket, and we have 10 terms over here. See, it goes from 1 to 10. And the final term is going to be 10 ln a plus 10 ln a, which gives us the final term on the right hand side. So that's a quick way to show, I suppose, that these two expressions are the same. Or you could simply just add up all the numbers and compare both sides. Three natural numbers a, b and c such that a squared plus b squared equals c squared are called a Pythagorean triple. Here we have three expressions for a, b and c. Pick one natural number n and verify that the corresponding values of a, b and c form a Pythagorean triple. So let's pick n equal to 2. N has to be a natural number, positive integer. So 2 2s are 4 plus 1 is 5 for a. B is going to be 2 times 4 is 8, plus 4 is 12. And as for C, we're going to get 2 times 2 squared. Well, that's 2 4s are 8, plus 2 by 2. That's 8 plus 4 is 12, plus 1 is 13. So do these numbers form a Pythagorean triple? Well, if they do, then one of these numbers squared is the sum of the other two numbers squared. So, this links in with a right angle triangle, of course. If these numbers form a Pythagorean triple, well, the largest number should be the hypotenuse, and the other two sides should be 5 and 12. Well, this looks more like 12, and this looks more like 5. So anyway, this is a famous right angle triangle, 13, 12, 5. It is true that 13 squared equals 12 squared plus 5 squared. We get 169 on each side. So we've shown that for n equals 2 at least, a, b and c form a Pythagorean triple. In the next part we want to prove that the expressions for a, b and c always form a Pythagorean triple, provided that n is a natural number. Okay, so let's check this. So we have to take a squared and add it to b squared. So we have to simplify all of this. Square the first term, multiply the first by second and double. Square the second over here. This bracket square the first. That's going to give us 4n to the power of 4. First by second and double. That's going to give us 8n cubed, and square the second term here. That's 4n squared. So I've simplified here, and now let's look at c squared. Now we have three terms in here, so this is not a binomial, it's actually a trinomial. Okay, trinomials are three terms. So to square it out, we could group any two of them. So let's group these two and treat this as a binomial squared. So we square the first term, the 2n squared. Well, that's 4n to the power of 4. We multiply the first term by the second term and double the result. So 2n squared by 2n plus 1 gives us 4n cubed plus 2n squared. Finally, we square the second term. That's the 2n plus 1 squared. So we need to bracket that because it's got two terms, of course, and square it. Okay, so if you look at this expression and look at this expression up here, you can see that they're the same. Just cross out all the terms that are the same. 4n squared plus 4n squared is 8n squared, and the 4n and the 1 are the same. So now, using these expressions here, we found a way to generate right-angled triangles with integer sides. Okay, see, n is a natural number, and clearly a is going to be a natural number. If n is a natural number, 2n plus 1 is obviously a natural number. So a, b, and c are going to be sides of a right-angled triangle, where c is the longest side, or the hypotenuse. And those sides are going to have integer length, or, well, positive integers, or natural numbers. We don't have negative sides, of course.